And welcome, everyone. Happy Friday. Welcome back to class. I got out for a bike ride yesterday. It was warm and it was sunny. Spring is on the way, and I'm really excited about that. I'm also excited that we will be wrapping up topic 4.1, balancing redox equations, and ready to jump into 4.2, looking at something useful that we can do with redox equations. So go ahead and get settled. We are going to jump right in. Now, last class, we assigned oxidation numbers. This is a statistics accounting method, not statistics, an accounting method, to be able to attribute where those electrons are. It doesn't mean a full positive charge or a full negative charge, but it does allow us to keep track of what's happening in a reaction. We can have a redox reaction where something's reduced and something is oxidized. This can happen in an acidic solution or in a basic solution or even in a neutral solution. And there's a special type of redox reaction that's called disproportionation, and this is where we left off last class, where the same species is both oxidized and reduced. Some of those molecules are oxidized, some of them are reduced. And we can balance these types of redox equations as well. So last class, we balanced a redox equation in an acidic solution, where we can simply add H+ ions to the side that needs more hydrogen. Now we're going to balance a reaction in base. This also doubles as our disproportionation reaction. So when chlorine gas dissolves in base, it disproportionates. We need to balance this equation. Step number 1, make sure we actually have a redox equation. If we don't, it's not worth the effort of this more rigorous method. If you can balance a reaction by inspection, need 2 of here, need 2 of this, need 1 of this, need 1 of this, done, do that instead. But if we need to do a more complex redox balancing where we have to add water or H+ or hydroxide and combine different numbers of electrons being oxidized and reduced, well, then we need to do this more rigorous method. Well, chlorine, part of the sample of chlorine, is reduced to an oxidation state of -1. Going from 0 to -1 would be reduced. Well, in this hypochlorite here, the oxygen has a -2 oxidation number. The overall charge on this anion is -1. So we need to get from -2 to -1, and that change in charge is due to chlorine. So chlorine here actually has a +1 oxidation number. That's unusual, but we assign oxygen first and then chlorine, and we can see that some of this chlorine gas is also oxidized. So we have one reactant, some of it's oxidized, some of it is reduced. The first step now is to separate this into 2 half reactions. And this might feel a little weird, but we're going to have 2 half reactions where each reaction has the same reactant, but different products. And we will go ahead and write that out. Okay, so we have our 2 half reactions. Now we need to balance them separately. The next step is to balance all reagents. Is that in the room or outside of the room?
I think that's
The microphone? Okay. Okay, it was supposed to be fixed yesterday. We'll move to the handheld if we have to. Okay, so we need to balance everything that's not oxygen or hydrogen. For the oxidation half reaction on the top, I have 2 chlorines on the left. I need 2 chlorines on the right. For the bottom half reaction, the reduction half, 2 chlorines on the left. I need 2 chlorines on the right. I have balanced the other atoms. Next up, we will balance the water, or balance the oxygen. For my oxidation half reaction at the top, 0 oxygens on the left, 2 oxygens on the right. That means I need to add 2 more oxygens, and I do that by adding H2O. I now have 2 oxygens on the left, 2 oxygens on the right for my oxidation half reaction. For my reduction half reaction, the lower one, 0 oxygen on the left, 0 oxygen on the right. Don't break a good thing. We will leave it as it is. So now we're ready to balance hydrogen. If this was an acidic solution, we could just add H+. But we don't have excess H+ in this solution, so I need to add hydrogen by adding water to one side and then add hydroxide to the other side, because the net difference there is adding an H+. So I'm going to start with my top half reaction, the oxidation half. I have 2 times 2, so 4 hydrogens on the left. I need to add 4 hydrogens on the right. I'm going to add that in the form of 4 H2O. And then very quickly, before I forget, add 4 hydroxides to the other side. I now have my hydrogens balanced. On the bottom half reaction, no hydrogens on the left, no hydrogens on the right. We will leave it there. The next step is to balance the electrons, and I can only add more negative charge. I can't take away charge. For the top half reaction, I have a total of -4 charges on the left and a total of 2 negative charges on the right. I can only add more negative charge, so I'm going to add 2 electrons to the right-hand side. And this makes sense because oxidation is losing electrons. For the bottom half reaction, I have a charge of 0 on the left, -2 on the right. I can only add negative charges, so I will add 2 electrons to my reactant side. Now I'm ready to combine these 2 half reactions. I have 2 balanced reactions. We will go ahead and add them together. I need to make sure that the number of electrons being produced matches the number of electrons being used up. Last time we had to find a common factor. Today we don't have to because it already matches. Nice and simple. So I'm going to add these 2 equations together, and I'm going to factor out common terms. So 2 electrons and 2 electrons. Electrons don't actually show up. We don't write them down in the overall balanced reaction. I can see I have 2 water molecules on the left and 4 water molecules on the right. I can subtract 2 from both sides, which just leaves me with 2 water molecules on the right. I'll go ahead and rewrite the remaining pieces. I have 2 molecules of chlorine. So I can double check my charges. 4 total negative charges on the left, 2 and 2 negative charges on the right. I have 4 chlorines on the left and 2 plus 2 chlorines on the right. I have a balanced reaction, but it's not in lowest terms. I could take all of these coefficients and divide them by 2. Ideally, we have our redox equation in lowest terms. So I'm going to go ahead and divide everything by 2 to get my final result. Therefore, we now have a balanced equation. So we can see that this method is a lot more involved. It takes more time. But if you practice and learn how to do this method, it works every time. If you have another method that you prefer that works in both acidic and basic solutions, you're welcome to do that as well. So for analyzing redox equations, we now know how to assign oxidation numbers and balance these equations. Now we want to do something useful with that. I'm going to skip this part. So we're going to jump into topic 4.2 on our next slide. We now want to do something useful. We know that in a redox equation, electrons are produced and electrons are used up. If I put some solid zinc in a beaker with copper 2+ ions, the copper will become oxidized, or the zinc will become oxidized to zinc 2+ and produce 2 electrons. These 2 electrons can then react with the copper 2+ ions in solution to make copper solid. This is a picture of an experiment, the initial and the final conditions of putting this solid zinc and immersing it in a solution of copper 2+ ions. Well, over time, you can see the color of the copper 2+ solution becomes lighter. In the top picture, it's a really dark blue. The bottom picture, it's much lighter because the copper 2+ ions are coming out of solution and building up along the surface of the zinc electrode. So we have oxidation, we have reduction, we have the transfer of electrons, but besides making a less blue solution and building up some copper on the surface, we haven't really done much of anything useful. The electron transfer here has simply generated heat. It's made the solution and the materials a little bit warmer, but we haven't done something useful with these electrons. If we design an electrochemical cell, instead of like this, if we separate the place where reduction occurs and the place where oxidation occurs, we can cause the electrons to have to flow through an external wire. And if we get those electrons flowing through an external wire, well, that's current, and that's electricity. And we can do something useful with the flow of electrons. So where did this design to have a flow of electrons come from? There are 2 people that I'll tell you about today. Luigi Galvani, back in the 1700s, he was an Italian physician, and he was fascinated with anatomy. And the story goes that he was doing a dissection of a frog. This is the story. We know the outcome, but perhaps it happened like this. So he is doing this dissection of the frog, and he has a copper hook and an iron scalpel, and he hits a nerve, and the frog's leg twitches. And he says, aha, I have discovered something new. I have discovered animal electricity. Electricity comes from animals. And this was pretty fascinating, and he published a big paper about it and told everyone about it. Now, it is true that we do have a potential difference in our cells, and we do have communication in our bodies through electrical conductivity. So he's sort of right in that we do have this potential difference. The frog's leg really did twitch, but Alessandro Volta didn't believe that the source of this electricity was from the animal. He says, you know what, I don't think it was the animal, I think it was the tools that you were using that caused this electricity. And so he said, I'm going to prove it, and he did. He layered zinc and copper, zinc, copper, zinc, copper, zinc, copper in layers, and then he immersed that in a brine solution with some acid, some sulfuric acid, a soaked cloth, and then connected a wire, and he was able to cause the flow of electrons to spontaneously happen. He was able to cause zinc to be oxidized, and then something else was reduced. It was actually hydrogen that was reduced, not the copper. And so he was able to cause this flow of electrons. This was like the first battery, but it didn't last very long. This produced hydrogen bubbles, and the bubbles stopped the flow and the conductivity of the electricity. So it was really fascinating, it was really important, but it wasn't good enough to run our cell phones today. So John Daniell said, you know what if instead of just having the layers of zinc and copper, what if we also added the ion form of these metals? What if we added the cations, the aqueous forms of these metals as well? And Danielle was able to create this electrochemical cell. We call it the Danielle cell. An electrochemical cell is just any redox reaction that's designed so that we can have this flow of electrons. So we want to be able to analyze this cell, identify all the important pieces, and figure out what's happening in all the different areas and what's essential to make this electrochemical cell run. Let's start on the left-hand side, and this side is called the anode. The anode is where oxidation occurs. The anode is the name of the electrode immersed in the solution where oxidation occurs. These two terms are always paired. A way to remember that is an ox. There's an ox, just for your visual stimulation, okay? Anode is where oxidation occurs. So that means at this electrode, we have zinc metal turning into zinc cations, and electrons are produced. So the zinc solid atoms are coming off of that electrode and dissolving in the solution. Well, this produces electrons, and since it's set up in this particular way, rather than just immersing everything in one solution and the electrons just create heat from moving, we're requiring the electrons to flow through an external wire, an external circuit, over to the cathode. And the cathode is the place where reduction occurs. And at the cathode, we have the copper 2+ ions that are in solution, combining with those electrons that flow over to them to make solid copper. So the copper electrode actually gets bigger and heavier as these copper 2+ ions come out of solution. Now, from physics, you probably remember that an electrical circuit must be complete. We can't just have a break in it. So we require this salt bridge in the middle to be able to balance the charge buildup. We're adding cations here, we're losing cations here. This would run very briefly, if at all, because it would just have the buildup and loss of charges. So the salt bridge allows for the flow of ions to keep this charge balanced. And this closes the circuit. So let's just watch this brief video just for a minute to see an animation of this Danielle cell. It might take a second for the audio to kick in, but it should.
Let's zoom into the atomic scale and see how this cell operates. Here, at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter and the copper cathode heavier. Now let's close in to see the role of the salt bridge. The non-reactive sodium and nitrate ions of the salt bridge prevent the buildup of charge that would occur as zinc ions enter the anode solution and copper 2 ions leave the cathode solution. Such a charge buildup would halt cell operation. In the anode,
That's where we're going to leave it. Okay, so just a little animation to show us what's happening down at the atomic level. Now, this is the basis for any battery that we create or use. It has something being oxidized, something being reduced. It has an anode, it has a cathode. It forces this flow of electrons, and then we can put this battery in something to drive these moving electrons to do something useful, like light a light bulb or do anything else for our toys or our tools. Now, we want to be able to communicate important features of an electrochemical cell. But we don't want to have to draw out 2 sloshy beakers and a salt bridge and alligator clips with the wire. We want to be able to have a way to communicate this briefly and quickly, and ideally on an old typewriter. So what we want to do now is communicate this in the form of a cell diagram, where it takes one line of text on your computer screen, and we don't have to draw in the beakers and the salt bridge. But we need to be able to speak the same language and know how to write and to interpret these cell diagrams. So the first thing to know is that the left-hand side is always the anode, while the right-hand side is the cathode. The way I remember this is that this is alphabetical order. A comes before C. The anode and the cathode are separated by a double straight line, and this is a representative of the salt bridge. We also have these single straight lines showing a phase boundary. This is where we would show the difference between a solid and a liquid, or an aqueous and a gas, or even 2 different solids. Now note that liquid and aqueous can exist in the same solution. So if something is in the same solution, we simply separate them by a comma. So a straight line for a phase boundary, gas to liquid, solid to liquid, but then a comma to separate items that are in the same phase, that are mixed together, like aqueous and aqueous, or aqueous and liquid. We also require electrodes. We require a solid material that can conduct electricity. In this cell, the zinc is a solid metal, and copper is a solid metal that can conduct electricity. If we were doing this in the lab and we had little alligator clips, we could clip the alligator clip onto this solid metal. But not every redox reaction has a solid material that can conduct electricity at both the anode and the cathode. So sometimes we need to have an inert electrode. Inert means it just doesn't react. Something like platinum. We could add that as the solid material that we can clip our alligator clip to. It can be the site of the anode, or it's the anode or the cathode, it's the site of the oxidation or reduction, but it's not being oxidized or reduced itself. It's simply conducting the flow of electricity. So platinum is often used, or carbon solid graphite can also be used. So let's go ahead and practice and draw some cell diagrams. Let's start with part A. We want to take this balanced redox equation and turn it into a cell diagram. Here we're told that we need to use inert graphite electrodes because we don't have a solid metal material that can conduct electricity. First thing we need to do is decide what's being oxidized and what's being reduced, so then we know what our anode and cathode are. So assigning those oxidation numbers, chlorine 0 going to -1. 0 to -1 is a reduction in the oxidation number. Meanwhile, bromide is going from -1 to 0. -1 to 0 is oxidation. So I like to start with my salt bridge. I put that right in the middle. I've identified the bromine as the oxidation area, so that's my anode. That means bromine needs to go on the left-hand side of my salt bridge. So on this side, I have my bromide ion, and in solution with it, my bromine liquid. Aqueous and liquid are classified as the same phase. They mix together, so we can have a comma between those two species. But then I also need an inert graphite electrode that's solid, so I need a phase boundary to separate that side. The inert electrodes go on the outside of the cell diagram, so the furthest to the left and the furthest to the right. So that's my anode. And now I can do my cathode where reduction occurs. At my cathode, I have chlorine gas, and then I have chloride aqueous. Gas and aqueous are different phases, so they have a straight line to separate them. And then I also need my inert graphite electrode, so another phase boundary with my solid carbon. Notice that I didn't balance my redox equation in the cell diagram. We don't add coefficients. We simply add the materials, and the scientist interpreting this would be able to balance the equation themselves. Okay, let's do part B now. Here we have cobalt going from an oxidation number of 0 up to +2. 0 to +2 is oxidation. Meanwhile, we have iron 3+ going to iron 2+. 3+ to 2+, that is reduction. The reduction occurs at the cathode. So we'll start with the cathode this time. That means my iron needs to be on the right-hand side. I have iron 3+ ions and iron 2+ ions. They're both in aqueous phase, so they're simply separated by a comma. I can't clip an alligator clip to conduct electricity to iron ions. To solid iron I could, but I don't have solid iron. I only have the aqueous dissolved form, so I need to add a platinum electrode here that's solid. So that's my cathode. I can now do my anode on the left-hand side, where cobalt is being oxidized from a solid into an aqueous state. Cobalt can act as my electrode, so I don't need to add another inert electrode. I'd be able to clip my alligator clip onto this cobalt. I'll jump back to this if you're still writing, but part C is going to be our iClicker question. Which is the correct cell diagram for part C?
So you put the inner phase and you don't need.
The inert graphite electrode gives us a solid thing that can conduct electricity into the solution.
So you won't need.
That's right. So on the right-hand side, we needed the platinum because we only had ions otherwise. On the left-hand side, cobalt solid is a solid metal. It can conduct electricity, so I could just have a little bar of cobalt, and that would be the electrode.
Oh, okay, thank you.
Okay. Compare your answer with the person beside you and get your answer in 10 seconds. And 3, 2, and 1. Okay, most people went for C. C is the correct answer. We had a lot of votes otherwise, though. So we'll chat about this briefly. So I went in and highlighted the oxidation numbers. That's the first step. We have to figure out what's being oxidized, what's being reduced. That means we need to know the oxidation number change. Manganese is going from +7 down to +2. That's reduction. Red cat, that occurs at the cathode. Reduction at the cathode, red cat versus anox, anode for oxidation. So that means the manganese needs to be on the right-hand side because this is where my cathode is, the site of reduction. Part A also has the manganese on the right-hand side for the cathode. Part B and Part D do not, so it's down to A and C. But then we have to see if there's a solid electrode that can conduct electricity. We have aqueous and aqueous species, and we have the hint of inert graphite electrodes. So we need to add the carbon solid graphite electrodes to the outermost points of this cell diagram. Okay, so that's how we chose C. If we design a redox reaction strategically and cause and force the electrons through an external circuit, we can create electricity. If a reaction will create electricity, that means it's spontaneous. We need to be able to know if a reaction is spontaneous and what the potential difference of that reaction is. Is it a small voltage where the electrons will flow over, or is it a really big voltage that's going to drive and pull those electrons to force current to happen? So what we need to do now is learn how to calculate cell potential, how to calculate the voltage of a battery. If you buy a AA battery, depending on what it's made of, it might have a voltage of 1.5 volts. The lead acid battery in your car, each cell is about 2 volts to give an overall 12 volts. We need to know how to measure this potential difference. The potential difference between two sides, the anode and the cathode, depends on the materials that are producing that anode and the cathode. It also depends on temperature, and it also depends on concentration. For this Daniell cell that we were looking at before with zinc and copper, if we hooked this up to a voltmeter and measured the potential difference between the cathode and the anode with 1 molar solutions at 298 Kelvin, or 25 degrees Celsius, the voltmeter will give a cell potential, a standard cell potential, because this was done under standard conditions of 1 mole per liter and 25 degrees Celsius, of 1.10 volts. This is a spontaneous process. It's going to cause the flow of electrons to occur. We can consider the voltage of a cell like the height of the waterfall. And then flowing over the waterfall, we have the electrons. The electrons can flow with a little potential difference or a big potential difference. We want to measure voltage at this point, the difference between the anode and the cathode. To do that, we're going to use standard potential values. Just like when we were looking at heats of formation. Do you remember back to chapter 2, delta HF, the enthalpy of formation of any compound or material, and it was defined as producing something from elements in their standard state. We got away with doing that because we defined elements in their standard state as having a delta HF of 0. That was just our arbitrarily decided 0 ground point. Elements in their standard state were 0. Well, for standard potentials, we have a new ground 0 point. If we have a 1 molar solution of H+, so a 1 molar solution of acid, and we're using a solid platinum electrode, and in this solution, we have a 1 atmosphere concentration of hydrogen gas. This combination of 1 molar H+, 1 atmosphere of H2 gas with a platinum electrode is defined as the standard hydrogen electrode, or SHE. This has been arbitrarily decided as ground level 0. Every other electrode is going to be compared to hydrogen, and it could have a higher potential or a lower potential compared to hydrogen. We can write this out as an equilibrium with our 1 molar H+ and our 1 atmosphere of gas. And this is being defined as 0. So what scientists have done is taken this standard hydrogen electrode and then on the other side added all sorts of other materials. Solid iron immersed in an iron 2+ solution. Solid copper immersed in a copper 2+ solution. And a whole bunch of combinations on the right-hand side. And then recorded whatever the voltmeter spit out at them. So for example, we could take this standard hydrogen electrode. In this standard hydrogen electrode, put in some copper and a copper 2+ solution. On the left-hand side, we still have our standard hydrogen electrode. But when we do this, and we just set it up, spontaneously electrons will flow, and the voltmeter will read plus 0.34 volts. Scientists then took this plus 0.34 volts and put it into a table of values, standard potentials, that we're going to learn how to use and manipulate. We can look at this cell and analyze what this plus 0.34 volts means. It's a comparison to hydrogen. Every comparison is going to be to hydrogen, so we can compare apples to apples moving forward. Based on this setup, because this is a positive number, that means that when this is prepared like this, it just so happens that copper 2+ is more likely to be reduced compared to H+. H+ could have been reduced. Copper 2+ could have been reduced. One of them is going to be reduced when we set this up. With copper, it just so happens that copper 2+ will be reduced, which means the hydrogen is oxidized. Copper 2+ is more likely to be reduced than H+. How do we know that? Well, because it has a positive standard potential value. If copper 2+ is being reduced, that means it's causing something else to be oxidized. This means that copper 2+ is a stronger oxidizing agent compared to H+. So given the choice, which one is going to be reduced? It's going to be copper 2+. What does that mean? Well, that means copper 2+ is a stronger oxidizing agent than hydrogen. And we're going to see this value in this nice table of values in your workbook. Right here, we have a standard potential table of values. And it's going to be in your best interest to get very familiar with looking up data in this table. Here we have copper 2+ in equilibrium, and the measurement from the voltmeter when scientists did this experiment was plus 0.34 volts. We're going to come back to this table in a moment, but for now, see that the really negative values are in the top left. There are 3 columns. You read them down this way. And then the most positive values are in the bottom right. If we could have aligned this in a perfectly tall column, we would have, but it didn't fit on the page. So that's why it's in 3 columns. There's copper 2+. The next one we're going to look up is zinc. And we know that zinc was also in this Daniell cell, one of the first batteries. But zinc has a negative value. So let's see what that means. If we immerse zinc in a zinc 2+ solution with a 1 molar concentration the voltmeter is going to read negative 0.76 volts. If you compare this image to the previous one, you'll see that the electrons have actually changed direction. This, whatever process is happening spontaneously, but it's now happening in the backwards direction. Zinc is actually being oxidized and going into solution, which means that H plus is actually being reduced. Given the comparison of H plus and zinc 2 plus, if we set it up, which one's going to be reduced? Well, now it's H plus that will be reduced. Since it's more likely to be reduced, and it is reduced when we set it up like this, that means H plus now is the stronger oxidizing agent. So we need to know how to compare these standard potential values. Now I'm just going to go back. No, I'll leave it for a second. This cell potential, this half cell potential, because we compared it to the standard hydrogen potential, whatever number is more positive, or the more positive this half cell potential is, the more likely that species is to be reduced. If it has a really big positive value, like fluorine here, with its cell potential, half cell potential of plus 2.87, that's a really big number on this scale, fluorine is really likely to be reduced. That means it's a very strong oxidizing agent. That means fluoride over here is really weak at doing its job. If it was going to be oxidized, it would be really weak at doing that. It would be a weak reducing agent because fluorine is a really strong oxidizing agent. In contrast, we could find a really negative number. Na plus is a very weak oxidizing agent. It's very unlikely to be reduced. It's a weak oxidizing agent, which means going this way from products to reactants, it would be a really strong reducing agent. I think it's helpful to look at this on the table. Here is fluorine at the bottom with a big positive value. On this table, it's most likely to be reduced. That means it's a strong oxidizing agent. In contrast, sodium plus is least likely, or less likely to be reduced. Which means sodium is actually a strong reducing agent. So we need to be able to compare these values and know which one is strong and which one is weak. So take some time to play with this table and think about what this means. Now, you may have looked at this table before and called it a reduction potential table. So you may have learned that as well. All of these are equilibrium, so it can go either way. Years ago, this was called a standard reduction table. Now it's just called a standard potential table. That's the current convention, so that's what we're using. But if you want to call these reduction potentials, you're more than welcome to do that. But we will be calling them standard potentials. What we want to do now is learn how to take the difference of the two potential values. Again, we can imagine this as a waterfall, and we're going to go back to our Daniell cell. I've pulled out the two half cell potential values for the zinc and the copper. In this Daniell cell, we can see zinc is being oxidized. Oxidation occurs at the anode. copper is being reduced, reduction occurs at the cathode. If I were to put this on my waterfall, just to help visualize it, here's my plus 0.34 volt half cell potential for copper, and then my negative 0.76 volts for zinc. And then this would be my 0 volt for H plus and hydrogen. What I want to do is measure the difference between the cathode and the anode. The potential difference is going to be even bigger than if this was compared to the standard hydrogen electrode. If I was just comparing copper 2 plus to hydrogen, it would only be a plus 0.34 difference. But I want to go from this plus 0.34 all the way down to negative 0.76. The way that we calculate a cell potential is by taking the difference between the half potential at the cathode and subtracting the half potential at the anode. Now, if you learned this before as reduction plus flipping the sign of the oxidation, you're more than welcome to do that. But we're going to be talking about these as that potential difference. The electrons are going to flow over this potential difference, but we can calculate the standard cell potential. The standard cell potential is under standard conditions, so that means 25 degrees Celsius, 1 molar concentration, and 1 atmosphere of gases if it is included. Now, you may need to combine reduction and oxidation half equations and balance them such that these electrons balance. But if you have to find a common factor for the electrons, you never multiply the half cell potential the way that you multiply the electrons. The half cell potential is that potential, whether it's with 1 mole in your balanced equation or 2 moles in your balanced equation. We simply use the half cell potential. So when we come back next week, we're going to analyze these half cell potentials, solve cell potentials, and under non-standard conditions. Have a fabulous day. Enjoy some sunshine.